be electrochemistry. We're going to try something a little bit different and do a video style lesson. And then after this lesson, the only thing you have to do is the assignment that falls under it, all having to do with redox reactions. So I'll talk a little bit about that as we go through. So what we're actually going to cover here, I'll break it down a little bit, is what oxidation reduction reactions are, and then because of that we have a few key terms, but they kind of all overlap that we'll be using throughout the unit. So oxidation and reduction, and oxidizing agent and reducing agent. We'll go through a few reactions before putting in half reactions, and then we'll see that there's circumstances where we need to use something new called oxidation numbers. So first, before we get into all of that, let's just see what electrochemistry actually is, and so that we can define it. Electro meaning electricity, electron. Pretty much what we're dealing with here is we're looking at the flow of electrons within a chemical reaction, not just what the reactants are and what the products are. So we also want to see, and we'll write them out, where the electrons are actually going to and from. So the transfer of electrons from one substance to another. Okay, so oxidation reduction reactions. So we have a reaction here. We have copper with silver nitrate reacting to form silver and copper nitrate. So what we're seeing here is a single displacement reaction where copper is more reactive than silver, and it'll end up bumping it out of these bonds so that silver is now on its own as a product and copper nitrate is going to be together as a unit. So this will be reminiscent for the 4 C's from earlier in the first unit when we did single displacement reactions and we used the activity series. If you're in 4U, this is stuff that you did in grade 11. So we're going to have a lot of recap on that. So if we look at this more so as what's happening in an actual beaker when we put these things together, this chunk would be my solid copper. And anything that's aqueous, we know isn't actually really bonded, right? They're kind of existing as ions. So instead of drawing AgNO3 all together in this beaker, I've got the ions existing separately. So I've got separate silver ions and separate nitrate ions. So they're floating there, and they're the part that makes up the solution, this chunk being the copper. As we go through our reaction, we know that copper is going to be switching spots with silver, so that silver becomes a solid, and copper will now be part of this unit. So again, this unit being aqueous to us doesn't mean it's going to be pictured all as one piece in this solution. It's now, again, going to be nitrates existing on their own, floating around, and those coppers existing on their own, floating around. And those 2 pluses obviously came from that too. And I added something in this one. I don't know if you can see it, but we've now got some silver solid here, right? Obviously, this reaction would be ongoing, and there's way more ions in here that would continue the reaction as it goes. So that's what it's going to look like. Because we're drawing things as ions, I've got a new reaction down here in which I've taken those nitrates on either side, the silver nitrate and the copper nitrate, and put them to look like what we actually see in these beakers, where we have the silvers existing on their own and the nitrates existing on their own. Same on the other side, the coppers existing on their own and the nitrates existing on their own. So also just note right now that when we have the 2 in front of something, that 2 also ends up being for the nitrates, right? So we've got 2 silvers, but also 2 nitrates. Because we've got no numbers over here, there's no number behind the copper, so we just have the 1. The 2, as I said, came from that little 2. And we still have 2 nitrates because that baby 2 applied to it, right? So when we look at this, we can see that copper had a charge of 0. It was on its own and ended up becoming part of that unit with nitrate and has a charge. The opposite's true for silver. It started with a charge of 1+ and then ended up on its own, so it's a 0, it's neutral. but nothing ever happened to nitrate. There's 2 nitrates, it's always a 1- charge, and at the end there's also 2 nitrates, a 1- charge. So what we can do is we can actually take those out of our reaction. So what we had here initially is called a total ionic equation or reaction, in which we took absolutely everything from our original reaction and wrote it out into its ions. When we stroke out nitrate, because it's on either side, we call that a spectator ion. So obviously it's kind of like a sports analogy where this reaction's happening, it's a game, they're the players, and then the things that aren't doing anything are the spectators that are just watching and observing what's going on. So when we take those out, and I've rewritten it down here, our total ionic equation becomes a net ionic equation. And these are the things that really matter to us because they're the things that are changing in the reaction. You've got your copper charge changing from a 0 to a 2+, and you've got your silver charge changing from a 1+ to a 0. So what we can see is because those charge changes, it means we also have a transfer of electrons. So Cu, copper, is losing electrons because it's going from a 0 to a 2+. So if you gain charge, you're obviously losing something negative to become more positive. And if something is losing electrons, they had to go somewhere. So they're going to the silver. Silver is going from a 1+ to a 0. So it's going down in charge, it's gaining electrons. So here are 2 of those terms that we said we'd have to look at: oxidation and reduction. So oxidation is always going to be the loss of electrons, and reduction is going to be the exact opposite. It's going to be a gain of electrons. So often you'll hear these called redox reactions because you'll always have one thing being oxidized and one thing being reduced. You can't have 2 oxidation reactions or 2 reduction reactions because those electrons have to be transferred from something to something else. So there are a few tips for remembering that oxidation means losing electrons and reduction means gaining electrons. So 2 kind of sayings. The one I remember from high school is the first one, Leo the line says GER. So Leo stands for lose electrons oxidation, GER gain electrons reduction. Or oil rig, where oil stands for oil is loss, reduction is gain. Cool. So a couple more definitions while we're on that. They sound very similar to oxidation and reduction, so we've just broken it into a table as well. So 2 other ways of looking at it is that something can help something else become oxidized, or a substance can help something else become reduced. And in those terms, you either become an oxidizer or an oxidizing agent, or in the other way, a reducer or reducing agent. So you're an oxidizing agent if you help something else become oxidized. And you're a reducing agent if you help something else become reduced. So it's kind of repetitive because we're just putting a new term to the same stuff we just did with oxidation and reduction. So we've broken into a table. If you think back to a few slides, the copper ended up losing electrons, or donating them, if you want to think of it in that terms. So we knew lose is oxidation, and if you're oxidized, you help something else become reduced, so you're a reducing agent. And then the other thing in the situation, the silver, if those electrons went somewhere, they came here, they were accepted or gained. So if you gain electrons, you're reduced. And if you're reduced, you help something else become oxidized, so you're an oxidizing agent. So let's try to do one from scratch. So the steps for us are going to be, first of all, taking whatever our reaction is and writing it completely out. So taking our compounds and breaking them up into their ions for a total ionic equation. Step 2, we're going to just simplify it a little bit, kind of like when we took out those nitrates before. We're going to take out whatever isn't changing in the reaction. We'll take out the spectator ions. And then step 3, we're going to look at our charges of everything that's left behind and see what's gaining electrons and being reduced and what's losing electrons and being oxidized. So here's one done for us. We've got a few that you can probably pause the video and do on your own in a bit. But we've got zinc, it's a solid all on its own, being combined with copper sulfate. And on the other side of the reaction, zinc is now part of this unit, and we've got zinc sulfate, and copper is now sitting all on its own. So the easy ones to write out are always the things that are on their own, right? Like zinc, you don't have to do anything to. Copper on the other side still stands on its own. The hard part is trying to take these into their ions. So I really suggest you use a polyatomic ion chart so you can see their charges. It'll help you figure out the charges of other things, because copper is one of those guys that can be different charges, right? You can have a copper 1+ or a copper 2+. And so we can determine this is a copper 2+, because when we go to the chart, SO4 is going to be a 2- charge. And if that 2 didn't stick around and there's no other numbers, it would have been because that copper was a 2+, right? Over here, zinc on your periodic table, only one type, it's 2+, so at least that guy kind of helped us out. So we've got everything written down here. I accidentally missed my solid, but yes, zinc is a solid. And then to get to our net ionic equation, we notice that these sulfate ions don't change, right? They're always SO4 2-. So that is a spectator ion. They don't get to come down to step 2 because we've got zinc from 0 going to zinc 2+. There's a change. It's definitely not a spectator. And copper 2+ becoming copper 0. So obviously also a change. So it has to come down to step 2. So let's look a bit more of those charges at step 3. I've just kind of looked at them separately. We've got zinc being 0 going to zinc 2+. So if we're going up in charge, we're losing electrons. So we're losing 2 electrons because we're going up in charge by 2. And if you want to use either of those memory tools, oil rig or Leo the Lion, we know that oxidation is the term for loss of electrons. And then you just want to double check just to make sure you did it right. But if one thing's oxidation, the other has to be reduction. And let's just double check. So we are going from a 2+ down to a 0 charge. So if we're going down in charge, we must be gaining something negative. We're gaining electrons. We went down by increment of 2. So yes, we are reduction. So perhaps pause the video now and just try these 3. And then I will have the answers on the next slide. So just to quickly go through it, we've taken our first thing. Obviously, the zinc and copper are still solids and on their own. The copper had this charge of 2 in the first one, so okay, 2, still an aqueous because those are the brackets it had. In chlorine, there's 2 of them because of that little 2, and the charge was a -1. On the opposite side, we've got zinc with that 2. In chlorine, there's 2 again. Make sure you bring that coefficient up with a -1 charge. I've stroked out the chlorines because there's been no change between them, right? There's always 2 chlorine, 1- ions. I've just tried to kind of simplify it into one row, just it's easier for me, where I'll connect the copper on either side of the arrow with a line and the zinc on either side of the arrow with a line. So let's look at copper first. We're going from a charge of 2 down to a charge of 0. So if we're going down in charge, we're getting something negative, we're getting electrons, and that stands for reduction. And if you're reduced, you're going to be the oxidizing agent. I just go short form. So if we know one thing, we know the other thing must be the opposite. If this is reduced, the other is oxidized and a reducing agent. Let's just double check on that. So zinc is going from a charge of 0 to 2+, okay? We're going up in charge, which must mean we're losing something negative. So we're losing electrons, and yes, we're oxidized or a reducing agent. The next one I actually didn't break up because this guy, silver sulfide, is a solid. So it actually wouldn't break up into its ions. So I've pretty much just rewritten the exact same thing and just supplemented their charges right on here. So we have no spectator ions because there's nothing extra, right? We can keep everything here. We've got silver with a 0 charge going to silver with a plus charge, and sulfur going from a 0 charge to sulfur with a -2 charge. So if we're going From 0 to +1 for silver, we're going up in charge, which means we must be losing something negative, or oxidized, or in other words, reducing agent. And just to double check on our other side, we're going from 0 to -2 for sulfur, going down in charge, which must mean gaining something negative, gaining electrons, reduced, or an oxidizing agent for sulfur. Our last one, kind of going back to the terms that we learned with, we've got a polyatomic ion. Polyatomic ions never change. So usually that's kind of your idea that you know that's going to be the spectator ion involved. So copper, similar to the ones we saw before. Remember, sulfate had a 2- charge. Copper can be either 1 or 2+. So we're going to pick a 2+ here because those 2's ended up canceling each other out, right? That's where we get the 2+ from. The others should all make sense, right? Magnesium is always going to be 2+. End up stroking out sulfate, just like we thought we would, because it's always going to be a 2- charge. We're left behind with the metals. And we've got copper going from a 2+ to a 0. So it's going down in charge, gaining something that's negative, gaining electrons, so it's reduced, or in other words, an oxidizing agent. And magnesium is going to be the exact opposite. We're going from 0 to 2+. We're going up in charge, losing something negative, and we're oxidized or a reducing agent.